Okay, this is the part two of first week. Right. Um, oops, it's not working. Ah, Still, I'm familiarizing myself with some new tools to record my lecture. So sorry about any delay. Okay. So in the second part of week number one, I, so in the second part of week one, I'm going to tell you some details, some exemplary materials you can find out in periodic table. So whenever you're classifying the semiconductor material, please come up with or please remember those three words: elemental, compound, and alloy. Again, elemental, compound, and alloy. So what is a main or one of the examples for elemental semiconductor? Well, definitely it is silicon or germanium. Okay, so you can find the silicon and germanium in periodic table here. And atomic number of silicon is 14, and germanium, the atomic number of germanium is 32. And here the carbon, its atomic number is 6. You know the meaning of the atomic number. So once, in case of silicon atomic number is 14, which means it has 14 electrons per single silicon atom. Well, definitely we won't use all the electrons of single silicon atom when we are making, when we are trying to flow the current to charge and discharge a certain capacitor, for example, a DRAM cell capacitor to store digital information. The charge should be stored and discharged out of the cell capacitor. And what is the switch to control the uh, total amount of stored charge in a DRAM cell capacitor? That is a switch or transistor. So the role of transistor in DRAM is to flow current into the DRAM cell capacitor. So once capacitor is charged up, we can say that it stores digital data 1, otherwise 0. Anyhow, we will cover up some more basics and details maybe May or June. Now, let's get back to the lecture note, elementary semiconductor material. So once a elemental semiconductor consists of or builds up with a single atom, such as silicon or germanium or carbon, then we can say that this semiconductor material is very elementary. Okay. The next one is compound. You know the meaning of the compound. In English dictionary, you may find out the exact definition for the word compound. But in the field of semiconductor device and materials, compound semiconductor material means you can choose one atom from column 3. Here, column 3. From column 3, please pick up, choose one atom. And in column 5, this is column 4. Column 5, you can pick up a arsenide. Then the compound semiconductor material is indium arsenide. Herein, uh, 101, 50%, 50%. Okay? So half and half of total material, compound semiconductor material, consists of half of it is indium and the other half of it is arsenide. Right? So in this case, we are saying that a 3,5 compound semiconductor material. Okay, and some student may ask, why not choosing atom from column 2 instead of 3? And what about choosing a silicon atom from column 6? That was 2, 6. Well, that is available. You can do that. Zinc is selenide. Zinc selenide. That is a 2, 6 compound semiconductor material. So whenever you have a chance to read out a research paper, some researcher has used the 3,5 compound semiconductor, which means they used uh, indium arsenide, such as they choose the two atoms each from column 3 and column 5. Okay, zinc selenide is another representative material for 2,6 compound semiconductor. Okay, then the last classification for semiconductor material is alloy semiconductor material. So alloy means kind of mixing up many things. So now you're free to choose of any atom from this black colored box. Let's do that. Say gallium, indium, this phosphorus, and arsenide. Then indium, gallium, arsenide, phosphorus. And the mixing ratio is say X% of indium, then gallium is 1 minus X, and arsenide is Y, then phosphorus is 1 minus Y. Okay, so these are four different atoms are mixed up together to build up a single alloy semiconductor material. Okay. So while I was explaining, elementary compound alloy semiconductor materials, some student may uh, get some kind of rule to build up the semiconductor material. Always group 4 is a main actor, kind of main actor or actress, right? So for given column 5, 4 is a kind of reference column. So whenever you're choosing a atom from column 3, because 3 is a 4 minus 1, right? So one step away from the column 4, then you should pick up the other atom from column 5 because it has a plus one step forward. Okay, 3, 6, this kind of combination cannot make up the working semiconductor material. Okay, so column 4 is reference, and once you choose your own atom from column 3, then next atom that you should choose up is should be from column 5 instead of column 6, 7, 8, blah, blah, blah. Okay, so that's the reason why whenever you're singing whenever you read out the research paper, someone is studying the compound semiconductor, then they are saying that this is 3,5, this is 2,6, right? Okay, so always column 4 in which silicon and germanium is marked there. Okay, and then in terms of alloy semiconductor material, you may imagine that how come we cannot mix up two atoms both coming from column 4, such as silicon germanium. Well, you're right, it is allowed to mix up two atoms both coming from column 4. And in real, silicon germanium has been widely used since 2003 by Intel Corporation to fabricate the P-type transistor to boost up the device performance in terms of mobility. Silicon germanium has been used into the source and drain regime. Then the whole mobility in the channel can be boosted up by more than 10% compared against the past CMOS device generation technology platform. So silicon germanium is still used in 22, 14, 10 nanometer CMOS technology platform. 7 nanometers, 5 nanometer CMOS technology platform, which is now available in market. Maybe in recent news, the recent EE Times news article said that Qualcomm, the Snapdragon X60 chip 5G modem application, that chip will be fabricated using 5 nanometer CMOS technology of a Samsung Foundry technology. Multiple bridge channel field effect transistor, which is a surrounded gate all around the type transistor. So still, silicon germanium in that very state-of-the-art 5 nanometer CMOS technology platform has been well adopted. For what? For boosting up the whole mobility to satisfy the target device performance, such as ID set, saturation, drain current. Anyhow, so alloy semiconductor material has been still widely used, such as silicon germanium. That is the representative one. Representative one. And another one is uh, alum, aluminum gallium arsenide. So these type and that one, those two are widely used for optoelectronic electronics. Okay. And herein, if you take a look at silicon germanium and indium gallium arsenide, phosphorus and aluminum gallium arsenide, you may be faced with this kind of question. Hey, this is alloy semiconductor, but we use the two atoms, and in this material we use the four different atoms, and aluminum gallium arsenide we have used the different atoms. So we need some other professional word to have to differentiate it. And that's true. So binary silicon germanium, no. Silicon germanium is classified as binary alloy semiconductor material. Okay, and this aluminum gallium arsenide indicates as classified as a ternary alloy semiconductor material, and that one is classified as ternary semiconductor material. Right. So in this lecture note, so please remember what the elementary compound alloy semiconductor materials are, and you can name representative semiconductor materials for each class. Okay, silicon germanium as binary alloy semiconductor, and indium arsenide as 3,5 compound semiconductor, silicon itself, standalone silicon, as elementary semiconductor material. Okay, then now let's take a look at the atomic structure of silicon. So only for the purpose of reference, let's take a look at the atomic structure of hydrogen as well. So as I told you, the atomic number here, atomic number denoted as Z for hydrogen is 1. So this means that it has a single electrons. Okay? Per hydrogen atom, it has a single electron. And what about the silicon? Well, the silicon, it has a total uh, 14 electrons. So 8 plus 2 plus another here, 1, 2, 3, 4. So total 14 electrons per silicon atom. So now you may understand the meaning of atomic number in periodic table. So the higher the atomic number is, the bigger the atomic the corresponding atom is. Okay. Then the next question is, if you take a look at the atomic structure of hydrogen, well, it has very simple structure because it has a positively charged particle plus single electron. That's it. And this free electron is roaming around with respect to the positively charged particle. How about the silicon atom? So 14 positively charged particles are uh, placed at the center of the atomic structure of silicon, and 14 electrons are moving around, but not randomly, but in the very limited orbit or limited lane. Those 14 electrons are moving around the center of the silicon material, silicon atom. Okay, so some details of how the electrons are spread out in this, quantum system that is kind of beyond the scope of this lecture. So, based on your, common knowledge, you have learned in general physics and general chemistry, uh, when you're a freshman, first year undergraduate student, you may have remember the quantum number, primary quantum number, n1 is corresponding to the very the lowest energy orbit. The very first orbit, which has the lowest energy state and the lowest amount of energy. And according to the Pauli exclusion principle, only two electrons can get into the orbit for primary number one, okay, n of one. And the orbit for primary quantum number two, based on Pauli's exclusive principles, 8 electrons can get into the orbit for the primary number two. Okay? So total 2 plus 8, total 10 electrons are tightly bound with the 14 positively charged particles. In other words, when you are operating DRAM NAND flash memory, the electrons which can flow current is nothing to do with those 10 electrons, because those 10 electrons are tightly, seriously tightly uh, bound, bonded with 14 positively charged particles. However, as you have seen here, the orbit corresponding to the primary number 3 is, more or less quite long distance in between 14 positive charge at 1 and the orbit for primary number 3. And the rest of the electrons out of 14, since we have used the 10 electrons to fill out uh, orbits for primary number 1 and 2, only 4 electrons are left. So those 4 electrons will get into the orbit corresponding for quantum primary number 3. Basically, the total number of electrons which can be filled into the orbit for primary number 3 is 8. Okay, simply speaking, 8 empty chairs are ready. However, only 4 electrons are left, so 4 out of 8 seats are filled with electrons. Anyhow, these outermost 4 electrons are the main actor and actress in making current flow. Okay, remember that the outermost 4 electrons of silicon atom will become or will play a key role in flowing current. So in that sense, please understand the atomic structure of silicon. 3s, 3p, 2s, 2p, 1s orbit. So you don't need to have some detailed knowledge of what the 1s, 2s, 2p. Just remember, orbit for primary number 1, 2, 3, and only 4 electrons, which has no chance to get into the lane, first and second lane. So those guys, those 4 electrons should fill into the third lane, which is corresponding to the orbit for primary number 3. So now let's more focus on the silicon atom. So as I told you, uh, 14 positively charged particles are placed at the center of the silicon atomic structure, and the outermost 4 electrons roaming around with respect to the center of the silicon atom, they are moving around. Okay, so herein, the outermost orbit, denoted as 3s and 3p orbits, are to be filled by 4 electrons out of 14 electrons in a silicon atomic structure. And following based on the general chemistry and quantum chemistry, people have found out that uh, the orbits corresponding for the primary number 3 has been split into 2 different orbits denoted as 3s and 3p. However, those are 2 orbits, 3s, 3p orbitals, are to be hybridized, simply speaking, are to be combined together and to form 4 tetrahedral 3sp hybridized orbitals. So if this sounds very complicated, just forget about it. That's not a big deal in understanding the uh, electronic components such as diodes and transistors. Only remember the 4 outermost electrons will become the main actor and actress in flowing current in digital computer. Okay, let's take a short break, and I'm going to upload the second movie clip, and I will get back to you soon.